Good morning, everyone. I think everyone's just about logged in there now, so I think I'll get started. We're just after 10 a.m. GMT here. Welcome again to the SOLAS for Missing Data Analysis webinar series. This is the 5th webinar in our series, and today we'll be looking at the combination method of imputation in SOLAS. My name is Andrew Grannell, Senior Statistician here at Statistical Solutions. And I have my colleague here, Eoghan Murphy, with us. The format for today is, again, you're all on mute, so just due to the volume of people attending the webinar, if you want to ask questions or anything, just put them through the text box provided by the GoToWebinar window there. And at any stage, if you feel the fonts or the text in the webinar window is too small, you can use the zoom feature on the top left-hand corner of the GoToWebinar window. Okay, so feel free to ask questions throughout at any stage of the webinar. Eoghan's here on hand to take care of any questions, and I'll be stopping to handle any questions that come in throughout the webinar too. So at any stage, feel free to pass along your questions and comments. Okay, so just the overview of this webinar today. So I'm going to recap on the methods involved in this combination method today. So we've got the propensity score method, the predictive mean matching imputation, and Mahal-Nobis distance matching imputation. All these methods are incorporated into the combination imputation method in SOLAS. I'm going to run through the methodology behind the combination method. I'll run through a worked example and some pre and post imputation analysis in SOLAS, and then I'll be taking questions and comments as well. And again, as I said, feel free to send in your questions and comments at any stage throughout the webinar. Okay, so just to recap as well briefly, the concepts that we've covered so far in the 5 webinars we've done today are to date. We've done defining missingness, which is the first thing you need to do when you're approaching your missing data analysis. We've split up our missing data into the various missing data patterns, such as monotone and non-monotone missing data patterns. We've covered 4 different approaches to imputation: the predictive model-based, Mahal-Nobis distance matching, propensity score method, predictive mean matching. Those 4 methods we've covered over the last 4 or 5 months. We've done a lot of pre-imputation plotting techniques and various post-imputation analysis methods too. So we've covered quite a lot so far. This is the second last webinar in this series. So I hope you enjoy this one too. So the first method I want to cover here in the recap is just the propensity score method. So say if we take 2 covariates, fully observed covariates, x1 and x2, and we plot them as so, we can map all the data into this format. And for instance, I have the missing data corresponding to the outcome variable y. The red dots signify the missing value for the outcome variable, and the blue dots signify the observed values for the outcome variable. So say we have a missing data pattern as so. What we can do is we can fit a logistic regression model to this data, and we get the best fit line for that using our regression techniques. And as I've shown here with the green lines, and essentially what we do is the regression model allows SOLAS to model the missingness using the observed data, and then using the regression coefficients from this model, SOLAS can calculate the propensity that a subject would have a missing value in the variable being imputed. So in other words, the propensity score is the conditional probability of missingness given the vector of the observed covariates. So given the observed covariates from the and the regression model, we can calculate a propensity that a case is going to have a missing value, and we can impute. So that was the propensity score method. We also incorporate the predictive mean matching method, which is how we approach this here. Is I have a plot again of the outcome variable y and a fixed covariate x1, and the blue dots on the graph here represent the observed values for the outcome variable y and the covariate x1. And then the red values on the x-axis there, they represent observed values for x1 but are missing for the outcome variable y. And what we do is we do a linear regression model here, and we project those values onto the model, and then what we do is we match the surrounding observed values, and we use them to impute to create donor pools to impute the missing values. So just to zoom in on that plot I just showed you, we match the closest observed values by projecting all the observed values onto the linear regression line, and as you can see here, if we project a missing value up onto the line and we project all the observed values onto that line, we take the closest observed values to that missing value, and we impute the associated observed values, corresponding observed values. We do not impute the model value. We impute the surrounding observed values. So the corresponding closest matching observed values to the linear regression model are used to form donor pools, and values are randomly drawn using approximate Bayesian bootstrap method from the donor pool to form the imputations. And finally then, the third method incorporated into our combination method is the Mahalanobis distance matching. And here this is based on characteristics that are defined by the researcher, such as age, height, income, depending on the study. The Mahalanobis distance is calculated for each missing case to all fully observed cases. The Mahalanobis distance is given by the equation, the first equation there, and where S is the covariance matrix, and then the closest Mahalanobis distance cases are then used to form the donor pool, and again values are randomly selected using approximate Bayesian bootstrap from the donor pool to create the imputations. So that was a quick recap of the three methods that we're going to be talking about that are involved in our combination method. Now, the full webinars on these can be located on our SOLAS for Missing Data website. So that's solasmissingdata.com. So you can find the previous webinars for more detail on each of these methods on the website. So I'm just going to do a comparison now of various parameters for the propensity score and the predictive mean matching methods. So how do these methods fare up with the level of nonlinearity? So if it's if the data is nonlinear, the propensity score matching method is insensitive to the level of nonlinearity, whereas seeing as we're incorporating a linear regression model into the predictive mean matching method, a poor performance exists if nonlinearity is high. So it is quite robust to nonlinearity, but if nonlinearity is high, then a poor performance will exist. Overlap between the outcome variable y and the fixed covariates. Well, both methods work best if overlap exists. So that means the plot that I showed you there for propensity score, where all the missing values for the outcome variable are encompassed in the observed values, that's when these matching methods work best. And then finally, for correlation between the outcome variable y and our covariates, well, propensity score matching performs better when the correlation is high between the outcome variable and the covariates, and this is not affected by when using predictive mean matching. Okay, so so that's our recap covered anyway. So when we took these three methods and we combined them, there was method to our madness, and it's it takes the best parts of each model and they compensate for one another, and we think it gets the best result. So so what I'm going to do now is I'm going to run through the methodology behind or the process behind the combination method. And essentially what we do is, and I'm going to keep this quite simple, is that the process involved in the combination method is, first you calculate the propensity scores for all the cases in the data set, and then once you have the estimates for the propensity scores, we then estimate the mean response for all the observed units and the predictive mean response for all the missing units using the predictive mean matching model. And then we take these and we run a Mahalanobis distance matching method using those two components, using the propensity score and the predictive mean response. So I'll just run through that again, and again feel free to ask any questions as we go along. So what we do is we first calculate the propensity score for each unit. We then calculate the predictive mean response using predictive mean matching method, and then we calculate the Mahalanobis distance between all the missing cases to all the observed cases using these two covariates as the fixed covariates defined by the researcher. Now, the properties then, moving on to the properties of this combination method, it inherits the original properties of the propensity score and the predictive mean matching method as we discussed before. But seeing as we're taking two separate approaches, we're taking a modeling approach and a matching approach, we can achieve double robustness, which is the combination of two approaches. We can achieve double robustness, and this is explained very well in a paper by Kang and Schaefer in 2007. Again, if you need the reference, just contact us. The correlation between the outcome variable y and its covariates is preserved, making this approach affinity invariant. And finally, under the current model and missing at random assumption, once they stand up, the combo method produces consistent estimates for the expected value of the outcome variable y and reduces the bias for the covariance between the covariance between the x covariates and the y outcome variable, especially when compared to the predictive or the propensity score matching below. So there's some quite nice advantages to using the combination method through double robustness, finally invariant, and also reducing bias in the covariance between the x and the y. So there are some quite nice properties here. So I think I'm going to move on now and show you a worked example in SOLAS. I'm going to do some pre-imputation analysis and some post-imputation analysis and compare the results before and after. So I'm just going to close out of this, and I'm going to open up SOLAS. So this is what SOLAS looks like. So I'm sure you're all familiar with it now at this stage. You can open a new data set in a spreadsheet format, or you can open an existing one. We have a script language window where you can type in your own language, or also you can run an analysis and alter the language to your own liking, or you can do different approaches. And also we have some plenty of help documentation there. So I'm going to open up this data set called treatment missing, and this data set, just a few comments coming in there. If the text is too small, you can use the zoom feature to zoom in on the GoToWebinar window if you want to zoom in on some of the the smaller text there in this in SOLAS. So here we have a data set with 9 variables and 188 cases. So we have age, height, width. We have treatment, if you were treated yes or no. We've measured your cholesterol value, and we've got 3 different dose types. Okay, so the first thing you always want to do when you're looking at a new data set is you want to see the missing data pattern. You want to see what the extent of missing data is. So we go to View Missing Data, and we can just click Use All to run it on all of the variables in the data set. So here we can see that the white cells represent the observed case, and the blue cells represent a missing data point. So this is for all 188 cases, so you can scroll down. Now if you have a large data set, that's quite tricky to do, so we also have this collapse feature which you can minimize the data set. So here now we've just collapsed all the rows, so we can see that we have 144 completely observed data set data points or cases. We have 42 missing this specific data point. We have 1 case missing these 2 data points, etc. Now we can also view the monotone, non-monotone pattern, where the red signifies the monotone pattern and the green signifies the non-monotone data points. Okay, so now we have an idea of what our missing data looks like and the patterns involved. We can also move on to looking at how the missing data is affected between the relationship of two variables. So we can view what we call a margin plot, where essentially it is a scatter plot with also some extra information about the missing data in the margins or in the axes. So I'm going to click Plot and Margin Plot, and as you can see here we also have scatter plots, histograms, box plots, etc. As normal. So I'm going to plot cholesterol versus dose 1 to see what the missing data characteristics are between these two, between the relationship between these two variables. So here we have our scatter plot, where the blue data points here represent observed data values. And then as you can see in the margins here in the axes, we have some other information. So the red data points here represent a observed value for dose 1, but a corresponding missing value for cholesterol. So we don't have the corresponding value for cholesterol. We also have a blue box plot here, which gives the representation for the distribution of the observed values for dose, and a red box plot which illustrates the distribution of the missing data points for corresponding data points for cholesterol. And again, likewise, we have 2 red dots here for they're observed for cholesterol but missing for dose 1, and we have a blue box plot and a small red box plot here. So this is interesting just to highlight the how the missing data points exist between the relationship between dose 1 and cholesterol. Now we can also split up this plot by a grouping variable. So I'm going to use the treatment variable, which is whether you were treated or not, so yes or no. So I'm going to split up into 2 separate plots. So now quite easily I've just created 2 separate plots. One for yes, this group were treated, and this group were not treated. And again, you can just see the distribution of the missingness. We can also see that there was no corresponding missing values for cholesterol in the treated group, and there were 2 in the not treated group. So these graphical features are quite handy when you're again exploring how missing data occurs in the relationship between 2 variables. Okay, so so I said I was going to do some pre-imputation analysis. So I'm going to do just a simple t-test between 2-group t-test. So what I'm going to do is I'm going to compare cholesterol values between the treatment groups. So I want to see if there's a difference between the cholesterol values of those who were treated and those who weren't treated. So I'm going to put in just a mean difference is equal to 0 to see if there's a difference or not. And I'm going to click OK. Now before I do that, I'm just going to say that SOLAS automatically checks the assumptions. So if it's not, if it doesn't meet the assumptions of a t-test, it'll run the associated non-parametric test. So I'm going to click OK. And now here's my results report. So what's reported here is N per group, so the sample size per group, and the mean value of each group, the standard deviation and the standard error. So here I can see that for cholesterol I have 146 cases, the mean value is 233.36. The no group has only 73 cases where the mean value is 222 and the yes group is 243. So we can see here there is a difference, but how much of a difference is there? And the p-value here is less than 0.05, so there is a significant difference between the two groups. Yeah, yes, treated yes and treated no. So I'm going to return to this now later. What I'm going to do now is I'm going to run our imputation. So go analyze multiple imputation, and we're going to use the propensity predictive mean matching Mahalanobis combo method. And similar to before, you can click and drag your fixed covariates to define the imputation into the fixed covariate box, and also the variables you want to compute into the variables to impute box. So I'm going to use these characteristics, age, height, and weight, as the fixed covariates to define the imputation, and I'm going to use I want to impute cholesterol dose 1, 2, and 3. I'm going to do 5 imputations. Again, as I said before, in SOLAS the minimum is 2 and the maximum is 50 imputations. I'm going to do 5 just for example purposes. And again, you can define various information about the non-monotone and monotone missingness, how you want to set up your donor pools. Do you want to use the 5 closest cases? Do you want to use the top 10% closest cases, etc.? And also various advanced options to do with seeding and so on. So we can click OK here when we're ready to run the imputation. It's going to run 5 imputations for me nice and quickly. So here now we have a new dataset window. At the bottom you can see there's one tab for each new dataset we've just created. And also we can see here that some of the values imputed are in red and some are in green. So this defines that the red imputed values are the monotone imputed values, and the green are the non-monotone imputed values. Okay, so now we have our 5 new data sets with our 5 complete data sets with all our imputed values. So now I'm going to run the t-test again now, the exact same t-test again, and see if the results have stayed the same or have changed. So I use cholesterol as the outcome variable, and I'm going to compare across both groups of the treatment variable, yes and no. Click OK. So now I have my output report again, and at the bottom here you can see something different, is that we have 5 output reports, 1 for each data set. Again, what's reported is the sample size per group, the mean value for each group, the standard deviation and standard error, and also then the t-value, degrees of freedom, and the p-value. So here we can see now that we have an increased sample size because now we have a complete data set, and also you can see that the no group is slightly increased and the yes group is slightly decreased. We also note here, which is very important, that the p-value used to be roughly 0.025, now it's 0.08, so now it's increased and it's gone above 0.05, so now it's become not significant. So now we're saying after we've included this extra sample size and these extra cases that we didn't include before, now we're saying we're slightly not significant, and there is no difference between the yes and no group. Again, we can look across the other data sets. Depending on the imputed values, you're going to get different values, mean values for yes and no, and different p-values. But across all 5 data sets, all 5 data sets are now saying that there is no significant difference between the 2 groups. So so that's just a quick example of some pre and post imputation analysis in SOLAS. Just going back to my slides, just a quick summary of that example there. So when we looked at the mean cholesterol value before and after imputation, it went from 2.33 with 146 sample size to 2.32 with a sample size of 188, so a slight drop. But then the mean treatment value, the mean value for the treatment group no, went from 222 and 76 people to 226 with 94 people. And the mean cholesterol value for the treatment group in the yes group went from 243 down to 238. And the sample size changed from 73 to 94 cases. Now the star here is just saying that, and this is the mean value across all 5 data sets, the mean value for each group. And also the p-value went from 0.025, which was significant difference, to greater than 0.05, which was a not significant difference across all 5 data sets, all the imputed data sets. So it's quite important to investigate missingness, and sometimes there's a bias in there that hasn't been accounted for, that when you do imputation analysis can slightly alter the outcome. So that's just what I wanted to cover this morning in our combination method webinar. I hope you've all found it interesting and useful. Just to give you a heads up as well, we've got 1 remaining webinar in this webinar series. We'll be having several more webinar series over time, but in this webinar series we've got 1 webinar left, which is sensitivity analysis, quite an important part of missing data analysis, and that will be next month in a few weeks. And also the next big conference we're going to is in at the end of July in San Diego, which is the big JSM conference. But we'll also be going to other conferences in the meantime. So if you're going to a conference, let us know, and we'll let you know if we'll be there too. It'll be great to meet, and if you have any questions or discussion points, we'd love to talk to you. So if there's any questions or comments you want to send in now, that'd be great. I'm just going to check with my colleague Eoghan here for some questions and comments and feedback. Again, as I said, all the previous webinars are on the solasmissingdata.com website. You can contact me directly at andrew.grannell@statsol.ie. My LinkedIn page is there, and my Twitter page is there as well. So I'm just going to quickly check with Eoghan on the question situation, and I'll get back to you in one moment. Okay, everyone. Just thanks again for all those questions and comments that were coming in. Eoghan pretty much had it under control there. I think most people have been responded to. So I think I'm just conscious of time at the moment. So we're slightly over time here. So I just want to say thanks to everyone again. We'll be putting up a recording of this webinar, and we'll be sending out the slides, PDF of the slides of this webinar again to everyone that attended. If you want to watch it again, or let something sink in, and you have a question at a later time, feel free again to email me or contact us through the website or anything, and we'll be happy to get back to you on any aspect or any questions you may have on missing data analysis and SOLAS or anything. So I'd just like to finish off again by saying thank you all for attending the webinars and the whole webinar series, and thank you very much for your feedback and your comments. Hope to see you next month.